All right, so let us continue. So we were discussing, right, the idea of having a Markov chain, right, model a Markov chain that tracks a pattern. So basically, right, this, well, while this is like a topic, right, is embedded in it many important, well, it's a subtopic, if you will, right, tracking a pattern, but it's embedded, right, embeds in it, right, is, well, within it, right, is many main topics such as, right, let's highlight again, efficient Markov modeling, right? So basically, the point, right, is that we've seen a theme that how you encode a state, right, in a Markov chain may make it into a Markov chain or not, right? So that's basically how much information you decide to put, right, or encode into a state, right? What you call a state. For example, remember the weather problem, right? Whether you encode one day weather, right, into the chain, call it 0, 1, or you encode 2 consecutive days, right, weather, call it 0, 1, 2, 3, makes a difference, right, in whether or not something is a Markov chain, okay? But on the other hand, right, so basically, if you don't encode enough information into the state, then it may not be a Markov chain. But if you encode too much, right, or sorry, yeah, if you encode too much, right, then actually what happens is your chain becomes, so you have too many states, right? You have more states than you need, and your transition matrix become big, right, in terms of dimension, and it becomes inefficient in terms of computation, and it also, right, basically gives rise to other awkward things, like you have to start the chain at, step 3, etc., right, in the example here that we have about the tracking, right, of the 3 coin toss, because basically, right, I mean, somehow the way we define it requires that we have to start at step 3, right? So that's one thing, right? So basically, we need to only model enough, right, to accomplish the purpose. That's the best, right? Not more, not less. The second idea, right, is the idea of an absorbing state. The absorbing state, right, has the characteristic that basically, right, if the chain is in an absorbing state, that means it must be in that absorbing state at or before, right, that time, right? So this, for some here, right, is an or statement. And so that would be helpful for us, right, to basically control the behavior of the path, right? Especially when we want to avoid, for example, let's say avoid, right, the absorbing state. Right, before time n. You see, once you have a state being absorbing, avoiding the absorbing state before time n is a very easy statement. Why? Because this is the same as saying that probability x sub n is, let's say, let's call the absorbing state, let's call a state, well, what designation we want it, right? Let's say state A, right? A for absorbing, okay? So if, or absorbing class, right? So basically, if we have a state or a class being absorbing, then the event, right, that xn is not in the absorbing state or absorbing class before n is the same, as saying xn is not in A, right, at that time only, notice, right? And we don't need to keep track of the whole path. Again, right, the logic is actually just negation, right, of the or statement. Remember, right, negation of the or statement becomes and, right? So basically, it's De Morgan's law in effect here, right? So if you're not at the absorbing state, right, at time n, that means you cannot be in the absorbing state, right, any step before time n, right? So that means you avoid the absorbing state all the time before n, okay? So that's the kind of like the point, right, of the absorbing state, okay? And then, you know, we kind of like summarize it here, right? Basically, the steps, right, you just look at a pattern and see how you progress into the pattern, right, rather than catching everything. Okay, turn whatever you want to pay attention to into the absorbing state. And then, right, notice that here, you can look at like initially as no pattern. That's state 0 right here. So that actually is kind of a, let me say, a subtle point, right? You want to think about it a little bit if you don't appreciate this point. That basically, right, remember, this seems like, right, it's tracking three coins at a time, right? However, it's flexible enough, right, to say that, well, it's not really just about tracking 3 coins at a time. It's actually tracking how much into the pattern, right, you are in right now. Okay, so therefore it allows for something like no pattern. So when you start, right, no toss, you haven't tossed yet. That also is equivalent to encoding no pattern. Compare again, right? Compare it with this huge matrix right here. Well, with this one, there's no way we can say that when you start with no toss, then that's equivalent to state 0. Because state 0 here is tell. Right? So in fact, here, every state has a definitive outcome. So it cannot, right, accommodate for starting when you have no toss, okay? So several things like that, right? That basically this example, right, is packed with a lot of things, right? A lot of information, a lot of points. So just pay attention to that. Okay, any question about any of these before we look at the problems? Okay. So I think, well, okay. So this one, right, would be a straightforward application of what we've just done, right? But let's see if we can redo it from scratch, right? So what will we need here? What's the first step? So the first step, right, is to model, right, the states. And here, right, is a run of 3 consecutive heads, so it's exactly as what we show you. So you have, right, state 0, 1, 2, and 3, right? Where 0 means no pattern, right? 1 is head, right, in the right place. Okay, so here, that's a lazy way to write it. But if you want to, right, be more careful, then 1 here, right, clearly is about head like this, right, and a tail, and then whatever here, right? And 2 would be head, tail, for example. All right, but notice, right, if you write like this, then it also kind of impose that, right, you have three outcomes, right, in your state. But that's not quite true. For example, right, this state two can accommodate head-head at the first two toss. That also count as state two. Do you understand? Or for example, right, state one here can also allow for a head in the first toss. Does it make sense? So, right, that's the flexibility of, this modeling. But that's why we need to be careful on what we write when we say head here, head here, right? So, I'm a bit lazy. I'm just going to write as in the right place or, in the pattern, right? But the meaning of it is kind of a bit more subtle. Do we understand? Right. So then you write the transition matrix, right? For example, right? No pattern going to a head, right? Would to pick up a head is P and then Q, right? And then P, if you have one head, right? If you pick up a tail, then you have no pattern, right? If you have two heads, then you will go to P, right? And then if you pick up a tail, right? So here, right? If you want, you can directly, right, turn the matrix into Q because state three, right, is what we are interested in. So we don't even need to think too much about, right, transition of state three back into the pattern, right? So we just could go directly there. And so the answer, right, within the first 10 flips, right, within is before less than, right? The answer is Q to the 10, 0, 3, right? Okay, any question here? Oh, sorry. I'm supposed to plug in numbers, right? So, 0.6 and 0.4, that kind of thing, right? Okay, so this one is a bit easier, right? It gives you a transition matrix already. Just ask you to address the question. So what should we do here?
Should we make glum an absorbing state?
Yeah, I think that's a good idea, right? He's not in a glum mood in the following 3 days. So let's try Q, right? Equals 0.5, 0.4, 0.1, 0.3, 0.4, 0.3, 0, 0, 1. Okay. And then what? What would the answer be with respect to Q? What would the answer be?
be 1 minus the sum where I goes from 0 to 1 of pi sub I and q to the third sub I3.
Then it's not 1 minus. Oh, he's not in a glum mood. Excellent. But I think the only thing you miss is he's currently in the cheerful mood. So there's
Okay.
yeah, right. So cheerful, we know exactly he's in state 0, right? Excellent. So the answer is 1 minus q cubed 0, 3. Right? 0, 2, right? Sorry. Okay. Any question about this? All right. So this one is a bit of a more challenging one. But now that you understand, hold on, let me see if you do understand. Yeah, no, it's fine. Yeah. All right. So this one, right, basically is trying to explain to you, right, in English what the question is, but simply, right, the question is right here. Prove it or give a counterexample, right? Where of course, right, QIM, right, YIM, because it goes from I to M, right? So let's, of course, right? I mean, if you kind of wiggle into this equation, then you just run into like a lot of things, right? So to do this kind of problem or any kind of math problem, I guess you want to take a step back and then see what's going on, right? What's the point of the question? First of all, right, let's ask, is there any hope for this proposal to be true? Or is the questioner crazy or, ignorant of probability, right, and Markov chain? Because if the question is not even to the point, then we can dismiss it and like, yeah, you don't even know what you're talking about, right? Is there any reason why, or right, put another way, based on what premise can we think that this has a chance to be true? Or, right, let me put it another way. Explain to me what Qij represent. Or, right, let's put it another way. Is there something like a Q matrix I can write down? Because apparently, right, notice what is this notation? This writes this and represent what? Q raised to the n, right? So it's really Q to the n I m right like that. So if I write down the Q matrix, right, what can I say about it? First of all, what is its dimension? What is the dimension of the Q matrix?
The state space is still infinite, right? Like the state space for P was infinite, unless I'm mistaken.
Was it? No one says that, right? I don't think so. So here, right, I guess it didn't quite say how many states the original Markov chain has, but for simplicity, you can say that, right? And again, this n notation is a bit. So let's say the state has n, right? The original state has n states, okay? To make it
Okay.
simple.
In that case, it's n minus one, big N minus one, because you're
Good.
only excluding the rth state.
Exactly, right? No R. Very good. Second, that's what I want. Second, right? And again, I think you made a very good observation that, could be infinite. But here's an advice, right? In abstract question like this, where the information is not provided, which is not here, or in a lot of cases, right, you can always consider the simple case first. Okay, it can be infinite or finite, right? Clearly finite matrix, I understand it more, I can visualize it better. If it doesn't hold for finite, right, forget about infinite. So things like that, right? We can always make some simplifying assumption. Of course, we have to be careful to see if we go away from the spirit of the problem or not. But if it doesn't, right, then we can always do more to test out the water, right, before we look at a general case. But here, right, I guess finite absolutely is fine because it doesn't hold for finite. Well, that's it, right? But yeah, so second is Q a transition matrix? Does Q legitimately satisfy a transition matrix requirement?
Yeah, because in the previous equation, all the probabilities are adjusted to remove the option of moving to R. So all rows should still add up to 1.
Perfect. You said it perfectly. The whole thing of 1 minus this, right, is just adjusting so that you exclude, right, moving to R, correct? So basically, the sum here of each row still sum to 1. And of course, each row is a probability, so it's not negative. So it's a transition matrix, right? Now, finally, actually now, right, I think actually the gentleman just, sorry, I guess you keep saying, what's your name?
I'm Nick.
Nick, okay. Yeah, Nick just said something very, very good, right? Which is the probability of moving, etc. So that's actually the next thing I want to ask. What is the meaning of Pij in terms of probability statement? What is it? Say the whole thing. What is it? What does Qij represent? In terms of X, right? I mean, I want the notation. Why? Because I want to compare it with this.
The probability that xn equals the jth state, given that x sub n minus 1 equals the ith state.
Okay, let's start with that. And I
And
guess,
time homogeneous.
say again?
This is time homogeneous, right? So it doesn't
Yeah,
matter
yeah.
what
No,
n is. Okay.
right. So I just like to move from n to n plus 1 rather than, so what you say is fine. But
Sure.
what you say is not correct, right? Because if it were this case, and this is PIJ.
Oh, sorry. Yeah, that's PIJ.
QIJ. I want QIJ. So that's a question. Can QIJ be interpreted in terms of X? Because, right, if it's not related to X at all, then again, right, the questioner's question here, whoever asked this question, is completely nonsense. But if it can be related to X, then there's some chance that he might be right. That person might be right, right? So that's why we're trying to find out what is the intention here.
Why would
What
the
is the state?
statement be wrong if we just said that I and j are not equal to r? So why would that statement be wrong?
Oh, you mean like this, and then you throw in the something IJ not equal to R, you said?
Right.
But where do you throw it in? Here, outside?
Sure. Just to extra.
Yeah, but if you read literally like this, translate to mathematics, isn't that just considering Pij, IJ not equal to R?
Yeah.
Which is really not, right? You understand? So
Yeah.
it's not the modification here, right? It's about the probability modification because you are modifying the quantity.
I understand. Okay.
Right, so what is it? All right, any suggestion before I tell you the answer? So it will be like Nick said, right? Notice, okay, let me just kind of guide you a bit further. What does this mean? This division by 1 minus PIR. What does it signal in probability, period? Whatever context, what does it signal?
You're normalizing the probability?
Yeah. Normalizing is not too informative. You can normalize in many, many ways, right? This is a special normalization. It happens in what? Okay, let me put it a little more bluntly. In what context of probabilities do we divide two probabilities? When we?
Condition?
Correct. So this is a conditional probability. And right, again, you can kind of follow a lot of clue and make guesses by just understanding what the formula usually says. So like PE given F is PEF over PF, right? That's definition. So the denominator usually denote what you're conditioning on, correct? So what are you conditioning on here?
J
Not
not
going to.
equaling r. Go ahead.
Sorry, I say that we're not moving to R from I.
Correct. So again, I think Kathy, right? What you say is still not precise because if you do that, you'll still fall into this trap, right? J not equal to R, okay? So that's not that. But what is it? It's in here. Or yeah, you can put J not equal to R inside the conditioning, but that's where it is. Do we understand the difference? So yeah, right, we're not moving to R. right? We know we're not moving to R. Do you understand? So let's show you, right? Because of course I can make all this kind of claim, but if I cannot prove my statement, then like what all I'm talking about is nonsense, right? So let's prove it. So is that true? Well, this is right by definition. Right, divided by probability. Correct? This is by definition. Now I will use the law of total probability, right? And condition on this, and also condition on xn equals to I on both, and multiply back, right? Probably xn equals to I, right? But you see that if I use the law of total probability, then the multiply back will cancel on both, right? So that will become probability xn plus 1 equals to j, xn plus 1 not equal to r, condition xn equals to I, divided by probability xn plus 1 not equal to r, condition xn equals to I. Do you understand? And now the top becomes Pij, as long as j is not equal to r, right? And the bottom becomes 1 minus PIR. Do we understand now? Any question? All right. So now that we saw this structure, we know what Qij stands for, then do you see at least some kind of logic how crazy it is to relate this to that? Note that. You understand? So now, right, the second question is, having said that Qij is a transition probability, right? Notice that we're saying that formally, as in sum to 1, blah, blah, blah. It may not, okay, I emphasize, just because it's a transition probability, it may not have a direct link to X in a meaningful way. Okay, let's explain. Even though it's a transition probability, right, I say it's yes, formally, but right, the meaning of it is right here. So let's compare it with this. And let me just say, right, and this is exactly where if you're just starting to learn Markov chain, it might make you a bit frustrated. Compare this with the regular context of Markov chain, especially with the context of avoiding, right, the absorbing state that we've been doing so far, right? These things. Okay? And explain to me if this is the same thing or not. Is this the same thing as we've been doing so far with the pattern tracking and absorbing state? And I've been advertising about how you want to avoid a certain state and things like that. Is this the same thing? Like, is this just a repeat of what I've been doing so far, right? We've been doing so far in the tracking and absorbing state. Just maybe a different way to write it? Yes or no? Like, you know, I was giving answer like, you know, q to the 10, right? 0, 3 here, things like that, right? Is that the same thing as this question? Any suggestion? All right, I'll give you a hint. The answer is no. They're not the same. And that's why this problem is also very good. You want to pay attention to this problem and understand why it's not what we've been discussing so far. And that's why whatever this technique is, right, whatever they write here, has a big question mark on it. But why is it not the same? That's what we've been discussing so far. Is it not also about avoiding a certain state, things like that?
Before we've been avoiding a state by using absorption, but now we're trying to avoid a state by just completely removing it from the matrix entirely.
True, but right, you could saying your way could be these are two equivalent ways to approach the same end problem, same topic, right? Who's to say no? Does that make sense? Like that's will be a question like, oh, I come up with an absorbing state technique, right? And well, it's valid, but let's say whoever here comes up with another technique, right? And maybe we're doing the same thing, right? Just two different ways to answer the same question. But that doesn't get to the harder problem, right? And my hint to you is no, we're not doing the same thing.
So you're posing the question where R is as an absorbing state, right?
Not really. You understand? The absorbing state is really a technique, right, to more compactly handle the avoidance, right, of going into state 3 before step 10, right?
Right.
You understand that this is for all of you, that I could handle this with a P matrix. I could do it with a P matrix. It's just very painful. Why? Because I have to like now use the P matrix to somehow describe paths that does not have any 3 in it. Right? I could. But combinatorially, how many paths do I have to do that? Do you understand? So it's not about the impossibility of doing with state matrix P. Absorbing state here is a technique to elegantly or beautifully, right, turn the question of, right, combinatorially having to list all paths that does not have state 3 in it into a easy calculation with a matrix with absorbing state. Does it make sense? So it's not absorbing state as a concept, but absorbing state as a technique, right? That I'm using here. Do we understand? I mean, the only analogy I can come up with right now is you can do 2 plus 2 plus 2 100 times, right? And I guess, I don't know, a 5-year-old child might sit there and, you know, really add this up 100 times, right? And for sure that poor child might get wrong. Or me and you would know it's 200, but we didn't do it by, right, adding it 100 times. We do 2 times 100. So something like that, right, is also the absorbing state technique. It's not that you cannot do it the long way. It's just painful, prone to error, right? So it's not conceptual. The difference here that I'm pointing out with this new problem is actually conceptual. It's not technique. All right, let me not just keep the suspense any further, and let me tell you. The difference is in this statement. And it's important, all right? When you do probability, maybe you don't pay attention to these things, but it's important. What we've been doing so far, let's just even use this notation, is probability xn equals to m, xk not equal to r, k from 1 to n, given x0 equals to I. That's what we've been doing so far. That starting at state I move to state M, avoiding state R along my path. You understand? So in that sense, these are in the future. I want to control my future path. Wow. What this says is starting at state I, move to state M, but knowing somehow that I will, or I have, whatever that statement is, avoided state R along the path already. Is part of the conditioning. Do we understand? Another way, if you will, is P of E given FG versus P of EG given F. These are not the same. On one hand, you have known that G happened. And you just look at E. On the other hand, you don't know that G has happened and you calculate it. All right. And this may be a loaded question, but which context is a natural question to pose? And which is like a unnatural question to pose?
I think the
I
first
would.
more natural.
The first one is natural, correct? This one actually is a bit unnatural.
Because the first one, you're enumerating all paths from the ith state to the mth state that just don't hit R. So you're throwing away some finite subset of paths that hit that bad state R.
Right.
The second one, you're somehow able to see all future paths.
That's correct. So correct. So I would say that it's not about enumeration. Probably there's enumeration in the second case too, but it's about information. It's about time here, time tense here, right? I think it's more of that issue. That here, right? It has the flavor of moving from present into the future, right? And just dictating how the future should. I want to do certain things in the future, right? Well, everything here is in the future. But here, part of the future somehow is already controlled. It's already given, right? And that, when you think about it, is a bit weird, right? In terms of information flow. Now, having said that, I don't deny, right, that this is impossible to state, or there's no context, right, that this doesn't happen. In fact, right, there is a very important concept in math finance or in stochastic calculus called the Brownian bridge, where exactly what happens is you know that you start at a point at some time and you end at another point and you just move randomly in between. All right, so you condition on the two endpoints, even though, right, this is time, so you do kind of have the future endpoint being fixed. All right, so there's that. But again, there is a motivation there why you want to do such thing. And again, the only analogy I can have is math finance, where, right, things like bond price, right? Bond always end up with a fixed value because that's the face value you get at the end. right? While in between, it moves randomly, right? The price is random, right? Right now, the bond price is known, so it's a constant. In the future, we'll have a fixed value because, right? I mean, that's a face value. In between, the interest rate is random, right? So that's such a thing, okay? However, right, like I said, is context dependent, and you don't see this as much. So anyway, right? So I want to qualify the word unnatural here. I don't mean like asking this question is forbidden or anything like that. But every time you kind of somehow put the future into conditioning, that's a bit awkward. All right, let me just put it that way, right? So that's highly questionable. All right, and again, right, I'm going through the heuristic here. I'm not putting any definitive statement down, because of course, if you want to do definitive statement, then you can only do math, right? I want to kind of help you understand the context of this question and why, right? And also, right, here's another thing, right? I guess here's where I'm getting at. In terms of transition matrix, right? Does this look like a transition matrix? Like, okay, so I did claim, right, that Q is a transition matrix. I did claim that, but like I said, it's only from the point of view of like formally looking at it, right? What, or how do I want to say this? Does this look like the spirit of Chapman-Kolmogorov? That's more like what I'm trying to get at. Is this Chapman-Kolmogorov? Does it feel like Chapman-Kolmogorov to you? Right, where moving from here to there. Does it feel like Chapman-Kolmogorov? And why do I invoke Chapman-Kolmogorov? Because this Q to n power, right? Remember, this actually requires you to go back to Chapman-Kolmogorov and see why the matrix power exactly represents that kind of transition probability, right? It's so simple, you may not even remember it. But when you come to a complex case like this, then you want to go back and dig up the Chapman-Kolmogorov and see why it works there. But clearly, they're invoking Chapman-Kolmogorov when they raise the matrix to a power here, right? So does this look like Chapman-Kolmogorov? Linking these two together like that? My answer is no. Okay. So what's the spirit of Chapman-Kolmogorov? The spirit of Chapman-Kolmogorov is simple. You go from I to J with memory of I, and then once you're at J, you go from J to K with memory of J. So that's why to move from I to K, you just sum over all possibilities in between. Notice, right, that memory from I to J, memory at I, from J to K, memory of J, allows you to chain like that, right? But okay, that's again waving hand, but still, right, if you want to look carefully, you have to look at the equation, right, of Chapman-Kolmogorov and see where the law of total probability is used. But spiritually or spirit-wise, this is about just stacking memory up somehow in a weird way, right? It just keeps stacking memory of the future, right, up, and well, memory of future, right? That's a very weird word, with sort of like a one-step memory. This is a one-step memory, and then you just get like n-step memory, right? That's the best I can put it. Again, I already said this is an unnatural thing. So all this just leads to the suspicion that this is wrong. This doesn't hold. That's it. It doesn't hold. So this should lead you to look for a counterexample. All right. Again, right, you see, maybe you won't appreciate this and tell me that, why don't you just tell me that it's wrong at the beginning and tell me to look for a counterexample? Doesn't that save my time? The answer is no, right? That kind of that brute force approach where you just try your luck at some solution, I think is highly not recommended. You want to know why, right? This doesn't have a chance to hold before you look for a counterexample, okay? So my explanation on why, right, it doesn't have a chance to hold, while still, right, giving some credit to what this stands for, right, is the point that I want to make here. And also, right, to appreciate this problem, you want to see how it kind of attractively pull you into a Chapman-Kolmogorov, right? And the whole swapping of conditioning, right? So, like I said, if you appreciate this problem, you understand what it's trying to say, then you would kind of already master Chapman-Kolmogorov and the spirit of Markov chain. Okay. But if you kind of see this as like a tedious nonsense, then well, that's okay, right? All right. Any question here? All right. So having said that, right, there's nothing else I want to show you, but right, just construct something and do the calculation. All right. So finding a counterexample may not be trivial either. All right. But I suspect that many matrices, many examples you come up with will not work anyway. But you just take some time to put together, right? So you can use my example here. That's fine. That's why I show you. But I highly encourage you to find your own example and play around with the numbers, right? To check that it doesn't work. Okay. All right. Any question? And also, right, I think here with my example, I zone into two, make two an absorbing state to make my calculation easy, right? Notice that with the way the question's posed, it doesn't say what R has to be. So making R into an absorbing state also kind of exploiting that a little bit, right? It should be true for any kind of R. So I want to make R a bit more special and see what happens. Okay, so let me give you the quiz and then we will continue right after the break. Okay. Any question before we take the break? Take the quiz. Well, I guess I can only show you this. So the quiz will be a Gary's question, okay? Right here. All right. So let us continue after the break. Any question before we continue? All right, so we are done with lecture 6. Let us continue. So, right, as advertised, right, the natural follow-up topic to what we've been doing so far, right, is to compute path probabilities, right, of a Markov chain. Okay. So, on one hand, right, it should be viewed as kind of, you know, an extension, right, of, let's say, probability of x, let's say n equals to j, given x0 equals to I, right? This, you know, can be viewed as a path, right? But really, right, you just specify the beginning and the end of the path, right? You can definitely do much more, right? So, but that's exactly what we're dealing with here, right? A sequence of transitions, and then the main one, right, is how it enters or avoids a set of states by a given time, right? So this exactly is about, right, that kind of enumeration, right, that Kathy mentioned, that how do we do this efficiently under, right, different possible variations, okay? So we set out with, let's say, maybe, right, easy thing, but maybe not appreciated if you don't think of it carefully, right? Let's say I want a specific path, right? Let's say that I have a transition matrix, right? P, right? With, let's say, you know, not 10 states, right? All right. And let's say I want the probability of, let's say, right, starting at state 2, move to, you know, state 3, 5, 7, 9, and end up at state 8. Okay. You know, I'm too lazy to write down the whole thing, right? Like that. Okay. Does that make sense? That's the probability I want. Let's test our understanding here. Given the transition matrix P, can you tell me, or is it possible to write down what this probability is? What's the probability I move to that specific sequence of state in those steps?
You just multiply each of the transition probabilities, right? In a sequence. So probability of x, actually you can't do that because you have to, like, it's like probability of x5 being equal to 8 conditioned on x4 being equal to 9, x3 equal to 7, x2 equal to 5, blah, 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 times then x4 conditioned on the state desired for x3, x2, x1, and x0, and so on and so forth.
Yeah.
But
So,
we don't know all of those conditional probabilities. We only know the one step. But I mean, by the Markov property, you can eliminate.
yeah, no, you just said everything perfectly, right? So basically, that's exactly it, right? So basically, remember, right, there was at one point I told you about the multiplication rule, right? Let's say something like P, right? Let's say E1 up to En, right? Is P of En conditioned on En minus 1, E1, right? Times P En minus 1, En minus 2, E1, right? So on, right? PE2 conditional E1, P1, right? Exactly, right? This is the multiplication rule. And at that time, I explicitly said, right, that you cannot drop the conditioning, because, right, usually we don't have Markov. So, but here, right, from this point of view, exactly what we have is, right, is probability, right, x5 equals to 8 condition on x4, x3, etc. 0 times probable x4 equals to 9 condition on x3, x0, right, etc. Does that make sense? And so, right, basically, that's the multiplication rule, but we can drop all this previous conditioning by Markov property, leaving you with just a transition probability. So long story short, right, the question I'm asking here would be P23, P35, P57, P79, P98. Like that. Right. Again, right? Sounds simple, sounds intuitive, but right, note the whole machinery behind it. The Markov property, the multiplication rule, right? Things like that. Right? Any question? So that that's exactly right. Is what I'm trying to say here. Right. So let me just show you the slides, but that's all I'm trying to say. Like that, right? Well, so again, right, notice that this is the multiplication rule, right, together with the Markov property. Right. Okay. So yeah, so here, right, I just want to emphasize, right, when you want to calculate the probability of specific path, that's one sequence of transition, right? Let's say you start at 2, you go to 3, go to 5, go to 7, then go to 8, right? Well, if you do, let's say 1, 2, 3, 4, right? P to the 4 to 8, then you're looking at all possible paths, right? Moving from 2 to 8, right? Moving through all the states, right? This is so P to the 4 to 8, look at all possibilities, right? To move from 2 to 8, ignoring, right? Whatever in between. Is that okay? All right. So now that's the easy one, right? We just kind of go through it. Now, here's the more complex one, right? So we have a Markov chain, right? But now we want to calculate probability that it enters or avoids a set of state by a given time. Okay. And this, right, generalizes a pattern tracking Markov chain we discussed in the previous lecture. And the idea, right, is exactly that kind of transition from P to Q we've been discussing so far. Okay. So basically, you try to construct a new chain that has all the states, right, that except the one that you focus on, and a new absorbing state that basically represent, right, so notice, right, the dimension of W and N are not the same, right? Not the same dimension. Except, of course, right, when you only have one absorbing state, then, right, you also get one absorbing, so the dimension are equal. But in general, right, W might have a smaller dimension than X, right? So, right, this two chain behaves in the same way until, right, you first enter A. Once you enter, right, A, then you kind of get stuck, right, by the chain W. So you can use W to analyze, right, those behavior that got associated with the absorbing class. Okay. So here, right, it's important enough for us to kind of tell you how to write down the transition probabilities, right, of W, the modified chain. So the point, right, is that before you only have, let's say, one, right, you move from one absorbing state. So this is not necessary because, you just turn that into, right, 1 and 0 everywhere else. But if you have, like, let's say, an absorbing class, right, you want, let's say, to make 2 and 4, right, absorbing, then, right, this equation, right, is helpful. Okay, so I think it's just easier to look at an example, right, to show you what happens here. Let me see here. Well, okay, so let us look at an example, right? So let's say you have 0, 1, 2, 3, 0, 1, 2, 3, right? Let's make it 0.1, 0.2, 0.3, 0.4, 0.25, 0.25, 0.25, 0.25, 1/3, 1/3, 1/3, 0, 0, 1/3, 1/3, 1/3, right? I'm just making up numbers, okay? So this is matrix P. Now I want a matrix Q, right, in which I make 0 and 3 into an absorbing class. Okay, for what reason, we'll explain that later, right? Which one we will choose to be absorbing, we'll look at later. Usually, right, or they will always be the ones that we want to enter into our void, right, at a certain state, right, by a certain time, okay? But let's see here, right? Let's see, we understand here. If I want to turn 0, 3 into an absorbing class, right, from the original chain. So this is chain X, right? Chain W, right? What states do my chain W have to begin with?
1, 2, and A.
Mm-hmm. Good. 1, 2, and A, right? And can someone read me the first row of Q?
My guess is 0.2, 0.3, and then 0.5.
Yeah, 0.2, 0.3, 0.5. So now you see, it's the same if you're not there. If you start outside and you want to end up in, then you just sum up everything remaining. That's what it says. You understand? All right. So can someone read me the second row?
1/3, 1/3, 1/3.
And obviously that last one is 0, 0, 1. Right? So that's how you would write, change a matrix P to matrix Q in general, by choosing a certain set of states in absorbing class. Any question about this? All right. Now, so there are many, right, variations here that we want to consider. Again, right, the amount of variations might make you a bit kind of frustrated, whatever. But if you understand the principle behind it, they kind of all boil down to the same logic, really, right? But we just kind of differentiate to different states for some technicality issues that we'll explain. Okay? So the first one is to enter a set by time M, right here, right? So we want to say that you start at I, and you want to enter, right, a set of state before time M, right? Notice I is not in A here, right? So for, let's say for with the example here that we have, right? Then I want to start at state 1. And let's say I will want to enter state 0 or 3. Right. Before, let's say, time 10. Does it make sense? And I think, right, the answer is obvious here. What should the answer be in terms of the Q matrix that we just wrote now? It should be Q to the 10, 1A. Right? Or in general, right? This is Q to the 10, IA. Or Q to the M, IA. Is that okay? Right, so basically we're just describing it again, right? Any question? All right, so let's see. Can we try this? So suppose we have a Markov chain with states, right, and transition. We want to find a probability that the matrix or the chain, right, goes into a pattern 1, 2, 1, 2 within k steps. Right? Of course, k is, more than 4, right? So first of all, do we understand this scenario? This, right, is a more generalization than the, let's say, head pattern, right? Or head tail, whatever, right? That we looked at in the previous lecture. Because, right, if we look at head tail and head that kind of thing, essentially, right, what we're looking at from this context is you had a Markov chain that had transition matrix 0, 1, 0, 1, 0 to 0 probability Q, P, Q, P. Why? Because it's IID sequence, right? And you want to find the track pattern 1, 1, 1, or you're trying to track the pattern 1, 0, 1, 0 before a certain step. That's what we've been doing. Do you understand? So now, right, we want, so the possibilities of the states of the original one is expanded. So not only do we want to track, let's say 0, 1, 0, 1, whatever, right? We can track, let's say 1, 2, 1, 2, right? Or, God forbid, we can track 1, 2, 3, 4, right? Why not? We want to try to see the first time, right? Notice again, right? So the chain move around, right? The chain can take value 0 and then 3 and then 1 and then 4, 2, etc. Right? We want to know what's the probability that 1, 2, 3, 4 will appear, right, before a certain time. Does that make sense? Or 1, 2, 1, 2, whatever. Okay. So this is a bit of a jump, right? A little bit, but combining everything we've been telling you so far, right? You should be able to do so. So can you tell us what the first step to do here is? given the matrix P, right? You can take that matrix if you want, right? Sorry. You can take this matrix, right, if you want, right? It's P, right? So just some abstract P, doesn't matter. Yeah, so let's take this P, right? And I want to track the pattern 1, 2, 1, 2, right? I want to find the probability that 1, 2, 1, 2 appear, let's say before time n, right? Where n is bigger than 4. So what's the first thing I should do here?
Do you make that pattern an absorbing state? Or no?
Yeah, well, hold on.
I mean, I don't like the idea myself.
Yeah, but see, first of all, right? When you say that, you limit yourself to this discussion,
Right.
and you did not incorporate the pattern tracking discussion that we talked about in the previous.
Oh, okay, okay.
So, right, these are actually two techniques combined. Does that make sense?
Yeah.
So let me copy it into here. Right. So what should we do first? What we should do first is a pattern tracking matrix. Sorry, pattern tracking Markov chain. That's what you should do first. All right? Namely, Markov chain Y. Okay. Now, what states do Y have? How many states does Y have?
5 states?
Good, right? 5 states. Namely,
No pattern.
no pattern. 1, right? 1, 2, 1, 2, 1, 1, 2, 1, 2. Do we agree? Any question about this? And this is 0, 1, 2, 3, 4, right? For Y, right? So let's see if we can write down the transition matrix for Y. Can someone tell me the first row? What would the first row be? Or, right, if the first row is a bit hard to think about, how about, so namely, right, from no pattern. How about from state 1, namely having a 1? Is that easier?
Is going from 0, 0 is the very first entry 0.8?
Well, let's see what you have, and then we'll see the logic, right? Okay. So what do you propose? 0.8? So you still want to do the first row, right? Okay, 0.8, and then? Well, let's see if you explain that. Why 0 to 0.8?
Well, if you're building no pattern and you're currently at no pattern, you don't want to go to state 1. You don't want to go, yeah, you just don't want to, you just don't want to go to state 1. So you're okay with going to 0, 2, or 3. So you're summing those values, 0.1, 0.3, and 0.4 from the first row of matrix P.
Yeah, but that's the issue, right? Because here you are not, how to say this? By no pattern here, this 0 may not be connected to this 0 of the matrix P,
Oh, I understand.
right? Does that make sense? Because no pattern here means what? No pattern here means you could start at, I don't know, right? Either a 3 or right a 0 would all be okay, right? That's a no pattern clearly, right? If right now what you have is a 0 or a 3, that's no pattern, right? But actually, if you have a 2, right, and then you don't have anything before that, I think that's also a no pattern, right? As long as you don't have a 2, 1. Does that make sense?
Yeah.
So that might be a little bit hard to think about, right? So let's see if you can write down the first row. How do we go from the first row to other ones? Once we get a hang of that, maybe we can write down the other ones better. How do we go from state 1, right, of the pattern to other one?
Yeah, 0.5, 0.2, 0.3, 0. 0.
0.5, 0.2, 0.3, 0, 0.
Yeah.
All right. Could you explain? Let's say, how do you go from 1 to 1 with 0.2?
To go from 1 to 1, you just have to hit another 1 in the chain, which
Right.
I'm
So
sorry, I was looking
I think it's
I was looking at the
0.25, right?
wrong row.
Yeah.
Yeah, I was
Sorry.
sorry. I was looking at the wrong row.
That's my notation, right? So 0.25 here, right? Okay. And then I think this is 0.25, right?
Right.
And then this is 0.5, right? And 0, 0. Correct?
Mhm.
Do you understand? So no pattern, right? Oh, sorry. State 1 here means you're currently at a 1, right? And so to move to the second state, you must pick up a 2, right? So you move from 1 to 2, right? With probability 0.25. And then, right, you could stay at this if you pick up another 1 again, right? So that's that. But the rest, right, meaning namely moving from 3 to 0 will land you back on no pattern. So that's 0.5. Is that okay? Okay. What about row 2 then? Where can we go with row 2? If you're at 1, 2, right, then you can go to 1, 2, 1 with probability. One third, right? And then where else can you go? If you go to anything else, like 1, 2, 2, or what else? 1, 2, 3, 1, 2, 0, then you will go back to no pattern. Do we agree? Does it make sense? And then, right, from state 3, which is 1, 2, 1, right, you can move to 1, 2, 1, 2 with probability 0.25, right? But anything else, you would spoil the pattern, right? Agree? We'll go back to state 0. Correct?
If you
And
go
then 1,
back
2,
to
1.
1,
Oh,
Sorry,
you
if
know,
you go back to
no, no, no,
one,
no, no.
doesn't that?
No, you're right. You're right. You're right. Sorry. Yeah, this is my. I'm hasty here, right? Yeah. Thank you. So 1 to 1 here, you can pick up a 1 and then go back to 1, right? Thank you. That would be 0.25, right? 0.500. Correct? Thank you for that correction. Yeah, I can go back to state 1. And then, of course, state 4 is absorbing. So notice, right, the pattern tracking now is much more interesting than just a P and Q that we've been doing. Why? Because the original matrix, right, we start out with is much more complex, right? There's a dependency here rather than independent coin toss. That's what it is. So that's why the pattern tracking of a Markov chain, right, becomes more complex. Okay. Any questions so far? So what about no pattern? Is there a can we figure that one out? How does that
There's definitely going to be 3 zeros under 0, 2, 0, 4, and 0, 4, right? There's zero.
say again?
There's definitely going to be 3 zeros in the last 3 columns, right?
So
You
from
can't
no
pass
pattern, you cannot go to
either
to state
2, 3, or 4.
Yeah, that's a good observation, right? You cannot pick up from no pattern, you cannot pick up that many, right? Correct.
And so if you want to go from no pattern to state 1, I'm sure you have to sum some probabilities.
Yeah. Which is what?
Could you zoom out just a little bit? Because I think we
Sure,
lost.
sure. Sorry. I didn't show you that one, right? I think, right, here, we need to think about what no pattern means, right? What, am I still on? There was a flash of electricity.
We can
You
hear
guys-
you and see you.
Okay, cool, cool. Yeah, I had a battery, so. All right, so what was it? Yeah, sorry. We need to understand what no pattern here means, right? Or do we?
I think the confusing part is the extra 2, where if it's the very first times, if it's the very first 2, I don't know.
Wait, you mean this two or what two?
Oh, no. You were saying no pattern means right now we're at state 0 or 3. Definitely you're not having a pattern. But also if you're at state 2 and you haven't seen a 1 before it,
Yeah,
an issue.
I'm just trying to demonstrate that, right? That basically no pattern here includes quite a lot, right? Agree? So how do we capture that? Or I guess, yeah. It's not immediately clear to me how do we transition from no pattern to there, or is it possible to transition from no pattern to there? Okay, any suggestion before we see the answer? All right, so let's take a look. Right, so you want to, right, construct a tracking Markov chain, right? So for, right, oh, yeah, so state 0, yeah. Oh, so here, this is exactly what we missed. You see, that's exactly it. Yeah, we cannot lump together. You see, that's our state zero. That's our mistake. We can't lump them together. We need to separate them out because each of them have a different transition matrix into the other ones, right? That's exactly it. You see, 2 but not 1, 0, 3. That's why. So the mistake here, right, is that we are too greedy, if you will, and have a no pattern, single no pattern. So we may need to split this into better control. Does that make sense? So yep, like that. Okay, I guess I did not have an example. So let's just continue with this, right? So instead of having state 0, right, I would have, let's say, so 1, 2, 3, 4, right? So according to my interpretation, 5, 6, 7, right? So I will not, so let's see. All right, so let's kind of feel it again, right? So 1 to 1 is 0.25. 1 to 2 is 0.25, right? 0, 0. So we said 1 go back to 0 with probably 0.5, right? So now that we have 5, 5 is we are at state 0 before, right? 6 is we are at state 3 before. 7 is when we are at state 2, but not 1, right? So can we modify the first row now to 5, 6, and 7? Which one are we looking at?
For state 7, do you mean x sub n minus 2 not equal to 1?
Yeah, that's my terrible handwriting. I did write a 2, but I know
Oh,
it looks
okay,
like
sorry.
a 1. No, my
Okay.
bad. 2, yep. Right, so how do we do this? So 1 will go to 5 with probability 0.25, right? 0.25. Agree? So 2, right, will be 0, 0, 1/3, right? 0. With 2, we'll go to state 5 with probability 1/3. 2 will go to state 6 with probability 0. 2 will still go to state 7 with probability 1/3. Does that make sense? Three, right, would be 0.5. Sorry. 3 would be 0.25. 0, 0, right? And then 0.25. 3 go to state 5 with probably 1/3, right? Oh no. Wait. So sorry. I'm looking at wrong row. No, it's fine. 0.25, 0, 0.25. Right. So now we are state 1, right? 1 to 1. So 1 will go to 0 with probability 0.25. 1 cannot go to 1 can go to 3. Wait, hold on. Now I'm at state 1 to 1, right? If I go to 0, I have no pattern. If I go to 3, I have no pattern. But if I go to 2, I finish. So 1 cannot go back to state 7. So this is row 3.
Is
Right.
that the same case for row 1? Like, can row 1 go to 7?
one, you're right. No, very good, right? One cannot go to 7, but one would go to 2. Sorry. No, thank you, right? So one can go to where? Sorry, no, thank you very much. So one will go to where? 6, which is state 3. Oh, sorry, yeah. No, I think I messed that up, right? Yeah. Thank you. Right, thank you very much for pointing out. Does that make sense? Okay, so state 4 is still absorbing, right? So 0, 0, 1, 0, 0, 0, right? And then 5, 6, 7. Right, so 5, you're at state 0, right? So you can go to 1 with probability 0.1 or 0.2. And then that's it, right? You cannot go to other states, 0, 0, 0. You can stay at your pattern with probability 0.1, right? And then you can go to 3 with probability 0.3. And you can go to 2, right? Sorry, you can go to 3 with probability 0.4. You can go to 2 with probability 0.3. Does that make sense? Right, and so on. I think you can finish out, right, the last few rows. Right. So the point here is, right, no progress here in this particular problem needs to be broken down to more than just no pattern, because no pattern here has many previous leading up to. Each of this needs to be their own state. Is that okay? So that's necessary. We cannot lump them together, because if we lump them together, that's not going to be a transition problem. Any question about this? So, right, this technique of writing down, right, from a Markov chain, right, to a pattern tracking matrix is actually part of the technique here, right? The pattern tracking matrix will not be as simple as what we've been doing so far. So, any question you should ask here? Are we okay? All right. So, yep, that's it, right? And then once you do that, then basically, for example, let's say you start at state 6, and why state 6? Because 6 is when you start at 0, right? And then you want to go to, let's say, state 4 in that. So that's what that is. Right. I think here start at state 6 here, because in the beginning we said something like probably here, right? We need to say that we start a chain start with x0 equal to 0, so that the corresponding here would be q to the 6. Okay. We're good. Any question? All right. So that's one type, right, of path probability. Another type would be to try to find the probability of going to J without ever entering, right, a set. So basically, this is avoiding, right, avoiding a class of state, right? But the technique will be the same if you understand what's going on, right? You move from I to J, or IJ not in the absorbing class, and avoiding, right, the absorbing class throughout. And so once you have, right, the modified chain, then it'll just be Q to Mij. Because, right, A here is absorbing for the matrix Q. So if you move from I to J, then that implies that you are not within the class, absorbing class throughout your journey. Notice, right, again here, Ij is not in there. Does that make sense? All right.
Go up one slide. Sorry.
Yeah, go for it.
Thank
This
you.
one? Sure.
Yeah.
Right. So, for example, right here, you want to avoid state 3, 4, and 5, right? So you want to avoid state 3, 4, and 5. That's the same as saying, right, that the chain is less than or equal to 2, moving from 1 to 2, right? But so this in math finance again correspond to something called barrier option, where you have a stop, let's say start at 1, and you want it to move, right? You want to look at only events that the stock move from a point to another. Meanwhile, right, avoiding a certain kind of barrier. So it cannot move above this barrier throughout the entire journey. Okay. And so I guess here, I should have provided you with the original matrix P. I will do that, I guess, later on. But yeah, so here, right, this is the example from the textbook. So you can also take a look at the textbook, but I will include this into the slide, in the next lecture. But basically, right, once you modify this to a transition matrix Q, where, right, basically you preserve, so you understand, for example, right, the original matrix P, right, has 5 states, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? And according to this information, this is 0.3, 0.3, and whatever this is. And this is 0.1, 0.2, whatever this is, right? And then whatever this is. All you need, right, is these things to go into that, right? Because if it's 0.3, 0.3, this must be 0.4, 0.1, 0.2, this must be 0.7, the rest is just 1, right? So actually the information, all you need is there for the original, right? And then once you have this, then it's going to be Q to a 4th, 1, 2. Does that make sense? So again, right, this is the probability that the chain start at 1, right? Move to state 2, meanwhile, less than or equal to 2 during the whole path. All right, any question? Okay, so these, right, are not easy materials, right? So try to understand the spirit and try to kind of, right, see where the calculations come from. So we'll kind of repeat this a little bit next time, right? Just to make sure that everything sinks in and you understand the spirit. I'll provide the matrix P with clearer numerical values next time, so you'll see the transition from P to Q better. Okay, all right, then I'll see you on Wednesday.
Thank you, Professor.
Thank you, Professor.
I had a quick question, Professor.
Mhm.
Okay, yeah. I was gonna email you, but I decided I'll just stay till the end of class and ask. So
Yeah.
this Friday, so I signed up for Physics 2 this summer, which is completely asynchronous.
Yep.
And lectures are during our lectures, but because it's asynchronous, I've just been watching the recordings and coming to this lecture, which is synchronous, right?
Yeah.
And also I love math. But on Friday, we have our first exam scheduled during
Okay.
this time.
Alright.
I was wondering if it would be possible for me to miss class on Friday and watch the recording for our class later and then take a makeup quiz.
Well, I'll just excuse you for that one. But also be very careful if there's any conflict in terms of exam time. That might hurt.
Oh
But
yeah, I saw that the
lecture is fine. Lecture, yeah, I'll just give you the recording after we have it, and I'll excuse you for it. Okay.
Okay,
But
thank you so much.
exam time, we are not flexible because we are synchronous. So
Right.
I apply this standard to all students, right? So yeah, but lecture, yeah, that's fine.
Okay, I think that there's only one more exam for that class, but that isn't, but, oh, right, so our second exam for that class is technically the date of our final. I'll reach out to my other professor and request for a makeup in that class.
Right. Whatever you want to do with that class is none of my business, but like I said, our class is not flexible on that. Okay.
Like including the day of the final exam, correct?
Yeah, correct. I don't think we have a set time for our final exam, but it should be
August
centered
13th.
around the lecture time. Correct. Mhm.
Sure, okay. I'll discuss with the other professor regarding moving that exam then.
Okay.
No problem. Thank you so much for excusing me on Friday.
Sure. Yeah,
Appreciate it.
no worries. All right.
And I'll probably come into office hours for questions.
Sure,
but-
that's fine.
Okay, thank you so much. Have a nice day.
You too.